Mr. Harris here, and welcome back to another video. In this video, we're going to talk about giant covalent structure, some examples, and we'll do a quick recap. Alright, let's do the recap first. So in the previous video, we mentioned about the properties of giant covalent compounds. So for the physical state, we know that they are hard because of the presence of strong covalent bonds. Yes, some examples of giant covalent compounds are quartz, which is silicon dioxide, diamond as well. Of course, there are some others like graphite and so on and so forth. All right. For the melting points and boiling points, we know that they have pretty high MPs and BPs because, again, you need a large amount of energy to overcome the strong covalent bonds. And you'll notice the explanation is very similar to giant ionic structures. They also have a very high melting point and boiling points due to the presence of strong ionic bonds. How about the conductivity? So they're not able to conduct electricity. They're non-conductors. Of course, with the exception of graphite. Why is graphite able to conduct electricity? It is due to the presence of delocalized electrons. How about the solubility? They're insoluble. Giant covalent compounds, they're insoluble in both aqueous and non-aqueous solutions. All right. So let's have a look at some examples. So this is practice 9.3 on page 158. You can turn to your textbook and do it yourself and then refer to this video. All right, let's read the question. Solid silicon dioxide, SiO2, which another name, what's the other name? Quartz, yes. It melts at 1710 degrees Celsius, pretty high. While solid silicon tetrachloride melts at negative 70 degrees Celsius, so that's pretty low. Neither of the liquids formed conduct electricity. Question A1. Draw the electron diagram of silicon tetrachloride, showing electrons in the outermost shells only. Alright, so before I even start drawing, I have a question. Is SiCl4, solid silicon tetrachloride, is it an ionic compound or a covalent compound? How do you know? So of course, for me, I would use this as a hint. I'll use the melting point as a hint. So say for example, if this is an ionic compound, for ionic compounds they have giant ionic structures, right? So do giant ionic structures, do they have a high melting point or a low melting point? They have a high melting point, right? Because there's presence of strong ionic bonds. However, for this one, SiCl4 melts at negative 70 degrees Celsius. So from this, we know that it is a pretty low melting point. So what kind of structure has a low melting point? Yes, it's the simple molecular structure. So for a simple molecular structure, is it for covalent compounds or for ionic compounds? Yes, it is for covalent compounds. Right? Some covalent compounds, they have this structure. Alright, so now that I know it is a covalent compound, now that would help me in drawing the electron diagram. Alright, so you can pause the video and draw it by yourself. I'll show you the drawing now. So over here is the electron diagram of silicon tetrachloride. So silicon, because it has 4 outermost shell electrons, And chlorine, it has 7 outermost shell electrons. You'll see that they'll be sharing their electrons in this way. All right, so this is SiCl4. Okay, so let's read question 2. What type of structure does silicon tetrachloride have? So as I mentioned, it has a simple molecular structure. And what's the reasoning behind? It is due to the low melting point. All right, this gives us the hint. Okay, let's read question B. Explain the difference in melting points of the two compounds. Let me go back. SiO2, it melts at 1710 degrees, whereas SiCl4, it melts at negative 70 degrees. What's the reason? All right. The reason behind is SiO2, it has what type of structure? Yes, it has a giant covalent structure. And we know that giant covalent structure, a large amount of energy is needed to overcome the strong covalent bonds. So SiO2, it has strong covalent bonds present, whereas SiCl4, we know that it has a simple molecular structure. So comparatively, a small amount of energy is needed to overcome the weak van der Waals forces. Yes. The weak van der Waals forces. All right. So here's the answer. Silicon dioxide has a giant covalent structure, so a lot of energy is needed to overcome the strong covalent bonds. Silicon tetrachloride, it has a simple molecular structure which has weak van der Waals forces. So overall, silicon dioxide has a higher melting point when compared to silicon tetrachloride. Right? So when you write in full sentences, it will look something like this. But if you just answer these key points over here, you'll get the full marks. Okay? Let's read question C. Explain why neither of the liquids of the two compounds conduct electricity. Why don't neither of them conduct electricity? What are the reasonable explanations for this? I've taught you many times. It's because there isn't any mobile ions. So there are no mobile ions, and there aren't any delocalized electrons. All right. So do not contain mobile ions nor delocalized electrons. Let's do one more question. This is on page 173, question 23. Okay. Explain the following in terms of the structure and bonding of the substances being heated. So we need to explain it in terms of the structure and the bonding. Say, for example, the structure could be giant covalent structure, and the bonding would be strong covalent bond. All right, let's read question A. When a few iodine crystals are gently warmed, a purple vapor is observed. Now we'll need to explain it in terms of the structure. First, what's the structure in iodine crystals? Yes, it has a simple molecular structure. And what bonds are present there for a simple molecular structure? Yes, there are weak van der Waals force. So hence why just by gently warming it, vapor is being observed. Okay, now let's read question B. When a few potassium chloride crystals are gently warmed, no change is observed. So gently warming it, nothing happens. However, when very strong and prolonged heating is done, the crystals are melted. So potassium chloride. We know potassium is a metal, chloride is a nonmetal. So this is an ionic compound. So ionic compounds, they have giant ionic structures. So for giant ionic structure, we know that they have strong ionic bonds. Hence why strong and prolonged heating is required to melt the crystals. Okay, finally, very strong heating fails to melt a sample of silicon dioxide. Why is that the case? Of course, you need strong heating, you would also require prolonged heating, because silicon dioxide, it has a giant covalent structure. Giant covalent structures, they have strong covalent bonds present. So for strong covalent bonds, we know that a lot of energy and heat is required to overcome them. Okay, so here are the sample answers. So iodine, as I mentioned, it has a simple molecular structure. They only have weak van der Waals forces, so they could be easily overcome by gentle heating. Okay, for question B, as I mentioned, potassium chloride has a giant ionic structure. There are presence of strong ionic bonds, so it requires a lot of heat. Finally, question C, silicon dioxide has a giant covalent structure. There's presence of strong covalent bonds. All right, so I really like this question because it also helps us to recap on the previous structures and bondings we've learned: simple molecular structure and giant ionic structure. All right, this is the end of this video, but in the next video we'll be talking about the final one, which is giant metallic structure. And you can guess very easily, it is for metals. All right, so this is the end of this video. I'll see you in the next one. Bye.